Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about development of surfaces of solids. I am Dr. AIP Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now today we will be discussing about development of truncated square pyramid. So here you see we have a square pyramid available with us and a square pyramid of base 35 millimeter side. So the base edge is equal to 35 millimeter. Axis height is 60 millimeter long. That is the distance between O and O1. This distance is the axis height. So this is equal to 60 millimeter long. So it is resting on the base of it on the HP with two edges of the base perpendicular to the vertical plane. So these are the two edges which are perpendicular to the vertical plane. Now this square pyramid has been cut by a section plane which is perpendicular to the vertical plane and inclined at an angle of 45 degree to the horizontal plane, and it will be bisecting the axis of the square pyramid. So here you see this is an auxiliary inclined cutting plane. AIP cutting plane is there, which is inclined at an angle of 45 degree with respect to the horizontal plane, and this cutting plane happens to be perpendicular to the vertical plane, and this cutting plane passes through the axis in such a way that it bisects the axis of the pyramid over there. Now we are required to draw the sectional top view, then the true shape of the cut section as well, and we are also required to draw the development of the truncated square pyramid. So here we need to understand one thing. Since this is an AIP which is passing through the axis, bisecting the axis, so from the construction we will work out that this particular cutting plane, that is AIP, is going to cut all the slant generators. So there are 4 slant generators over here. So it is going to cut all the slant generators of this particular square pyramid. So 4 points of intersection will be there between these cutting plane and the 4 slant edges of the square pyramid, right? So let us start working out the projections of the solid to begin with. So since we are given that two edges of the base, they happen to be perpendicular to VP, so in a way basically other two, they will be parallel to the VP. So these two base edges, they are perpendicular to VP, and the other two, they will get parallel to the vertical plane. Now since this square pyramid is resting on its base in HP, so the top view which is obtained on the horizontal plane will provide us the true shape of the base of this particular square pyramid. So the side of the base is 35 millimeter. So we have drawn a square with base edge equal to 35 millimeter, and then once we join both of these diagonals over there, we obtain the axis point. So the axis point is O and O1. So O happens to be the axis point at the top, that is at the apex or the vertex of the square pyramid, whereas O1 is the axis point at the base of the pyramid. So the 4 you see vertices we have you see mentioned over here, A, B, C, D, these are the corners of the base. So once we have drawn the top view, now you can see this is one slant, you see triangular face, this is the second slant triangular face, this is the third slant triangular face, and this is the fourth slant triangular face. So all these 4 slant triangular faces, they will be visible in the top view, but we haven't darkened them because this square pyramid will be cut by an AIP in the front view. So we are going to darken these slant generators over there, slant edges, once the cutting has been done, right? So this is the top view of the uncut square pyramid. Now let us start working out the front view projections. So this is our axis point. From the axis, once we draw, now we can work out the front view over there. So axis height is given to us as 60 millimeter. So this is our axis line, and then axis, once we measure the 60 millimeter, you see height of the axis. So obviously point O dash will be located. That is the apex point of the square pyramid will be located over here. And then these are the base points A, B, C, D. So once you draw projector through B and A, so on the vertical plane, the projection of B and A will be obtained as B dash and A dash. And since it is resting on the ground, so the projections of B dash and A dash, they will be available on the XY reference line. Similarly, you draw the projections through C and D. So since the solid is resting on its base on HP, so the C dash and D dash points, they will be available resting on the XY reference line. So the front view projections corresponding to the base have been obtained. Apex point has been identified. Now we are going to join these slant edges of this particular square pyramid. And here once again we need to understand that projection for the slant edge will be dark or solid line because it is in the front face of the observer, because the observer is going to view the solid from this side. And the slant, you see, corresponding to this slant edge OA, the projection O dash A dash should have been dotted, but the projections of O dash A dash which are dotted or hidden line, they are, you see, coincided by or superseded by the dark line or the solid line projections corresponding to OB. So that is why we get a solid line projection over here corresponding to O dash B dash, superseding or overlapping the dotted line or the hidden line projections corresponding to O dash A dash. Similar, you see, concept applies here. That is the projection corresponding to OD, that is O dash D dash should be hidden, so this should be dotted, but these have been overlapped or superseded by the solid line projections of the edge OC in the front view. So O dash C dash, which happens to be the front view projection corresponding to this slant edge OC, they will be dark line or the represented by solid line. So they are going to supersede or overlap dotted line projections corresponding to O dash D dash. So here at both of these places we are going to get solid line projections corresponding to O dash B dash and O dash C dash, which are going to overlap the projections corresponding to O dash A dash and O dash D dash respectively. Now having drawn the front view, now we know that the cutting plane, it is going to bisect the axis, so we can measure this distance from the bottom or from the top. So this is the 30 millimeter distance. The moment I locate this distance, I locate a point on the axis, and through this point an auxiliary inclined plane, you see I have marked a point. So through this point an auxiliary inclined plane which will be inclined at an angle of 45 degree to the horizontal plane, this is going to cut the axis over here. So as it is passing through the axis, so all the four slant generators of the square pyramid, they are getting intersected. So 4 points of intersections we have obtained. And what are the names of these 4 points of intersection? So the names of these points of intersection, they are 1 dash, 2 dash over here, and 1 dash corresponds to the point of intersection of this cutting plane with the slant generator O dash A dash. Similarly, 2 dash happens to be the point of intersection of this cutting plane with the slant generator O dash B dash. Now I need to project these 2 points of intersections in the top view. So you see, I drop a perpendicular projector from point 1 dash, which happens to lie on the slant generator O dash A dash. So once I drop this perpendicular, wherever this perpendicular projection intersects with the top view of the slant generator, which is OA, so this point I will be obtaining as point number 1. Name of this point will be point number 1, right? So point 1 dash lies on the slant generator O dash A dash in the front view. You drop a perpendicular projection from 1 dash, and wherever it intersects with the top view corresponding to the slant generator OA, you get point 1. Similarly, from point 2 dash, which happens to lie on the front view of the slant generator OB, that is O dash B dash, So wherever the vertical projector is going to intersect with the top view corresponding to the slant generator OB, I get the intersection point as point number 2. Similarly, here I have another couple of points of intersection at this point over here with the cutting plane. So point 3 dash. So point 3 dash, it is the point of intersection of the cutting plane with the front view of the generator OC, that is O dash C dash. So the cutting plane is going to intersect O dash C dash at the point 3 dash. Similarly, the cutting plane is going to intersect the slant generator O dash D dash at point 4 dash. So from 3 dash and 4 dash, once again I am going to drop the perpendiculars, and wherever they intersect with OD, I get the point 4. Wherever this vertical projector intersects with OC, I am going to obtain point 3. So 4 points of intersections they have been located in the front view. 4 points of intersection they have been located in the top view. So once I join the POIs 1, 2, 3, 4 in the top view, that is once these points of intersections they are joined in the top view, so I obtain the sectioned top view corresponding to this cut surface or this section surface. But this is a much bigger surface. So since this section surface happens to be inclined to HP at an angle of 45 degree, so the top view, it does not give me the true shape, it gives me only the apparent shape of this cut surface, which is 1 dash, 2 dash, 3 dash and 4 dash. So I need to draw an auxiliary inclined plane parallel to this cutting plane to be able to obtain the true shape of this surface. But before that, I have joined the slant edges which are left with me after the cutting has taken place. So you see, these are the slant edges which have been joined dark after the cutting has taken place. So these are the projections for the slant edges which are remaining with me. Similarly, in the top view, 1A, 2B, 3C and 4D have been joined. Similarly, in the front view, 1 dash, A dash, 2 dash, B dash, 3 dash, C dash and 4 dash, D dash have been joined. So this part of the solid has been discarded because this has been removed away, right? So this has to be discarded over there. This is no longer available. Now, in order to obtain the true shape, I have to draw another auxiliary inclined plane x1, y1, which will be parallel to this cutting plane or which will be parallel to this section surface. So here you see we have couple of points of intersections on this generator, couple of points of intersection they are lying on these generators. So what I am going to do, I am going to draw projectors over there through 1 dash, 2 dash and 3 dash, 4 dash over there. So the projections from these 4 points which will be drawn onto AIP, they will provide me with the auxiliary plan projections on AIP. So since I am able to get auxiliary plan projections over here, so the distance of the plan, that is of the points of intersection in the plan, that is point 1, it will be this one. Distance of point 2 in the plan, it will be this one. Distance of point 3 in the plan from the XY reference plane, it will be this one. And distance of point 4 from the XY reference plane, it will be this distance. So these 4 distances I am going to plot and mark onto the corresponding locus lines for these points of intersections in the front view. So let us work these out. So please see, now I want to draw the first POI. So first POI corresponds to point 1. So please see, what is the distance of point 1 from the XY reference line in the plan? So this is the distance. I'll be measuring this distance and marking this distance over here. So name of this point is 1, 1. Then I will be marking the distance of second point. Just see, second point of intersection is this. So this is 2 point is located at this much distance from the XY reference line in the plan view. So the same distance has been marked over here. So the name of this point is 2, 1. Similarly, I need to mark another 2 points, that is 4. It is this distance. So point 4 is located over here. So this distance once I mark, so corresponding to the, you see, the bottom point of the base, this projector, that is corresponding to 4 dash. This is my projection line. So I'll be measuring this distance as it is equal to this distance in the plan view. And finally, point 3, it is at this much distance from the XY reference line in the plan. So the same distance I'll be marking from this plane x1, y1. So this distance I have to mark from the x1, y1 reference plane. So name of this point is 3, 1. So once all these 4 POIs have been obtained in the auxiliary plan view, so we can carry out the shading, we can join these edges over there corresponding to the section surface. So section surface edges, they are joined, and then this view, that is the auxiliary plan view, will provide us with the true shape of the cut section over here. So the true shape has been obtained. Now next thing is we are also required to draw the development of the truncated square pyramid over here. Now in order to draw the development, 2 things are required, that is true length of the slant edge. You see, either this slant edge or this slant edge. And another thing I require, second one, true length of the base edge. So true length of the base edge is available. Let me check, do I have the true lengths for O dash A dash or O dash B dash or O dash C dash or O dash D dash in the front view. So please check. OA top view projection corresponding to slant edge OA and O dash A dash, both of them, they are inclined to XY reference line. So it is giving me an oblique projection for OA. Similarly, OB edge, OB slant edge, top view is inclined to XY. Similarly, front view is also inclined to XY. So we can conclude over here that the projector that we have, it is having apparent edge even in the front view and even in the top view over there. Then third one, here you get, that is OC projector. In OC projector, once again, this is inclined to XY, and O dash C dash, that is the front view, is also inclined to XY. Again, it is an oblique line. Similarly, OD, this is also inclined, and O dash D dash is also inclined. Now, since all these projectors, they represent the apparent length in the front view and apparent length in the top view, so I am not getting the true length of the slant edge for this square pyramid over there. So what I need to do, I'll be using the principles of or the fundamentals of rotation of line to obtain the true length of this slant edge. So here you see, I have drawn a horizontal locus line from point O. Any one of the 4 edges you could have picked, either D or A or B or C. What I need to do, all these slant edges are available. I can pick up any one of these edges. So here I have picked up OC. So I have picked up OC. I am going to rotate this apparent length which happens to be inclined to XY line, and I have made it parallel to XY reference line. So this, after rotation, the name of the point is C1. And once I obtain this C1, what is the special characteristic about this apparent length? So the special characteristic about this apparent length is that this apparent length happens to be parallel to the vertical plane. So since this is parallel to the vertical plane, so its projection of point C1 onto the vertical plane will provide us with the true length for the slant edge O dash C dash over here. So where is the locus line for C dash in the front view? This one. So this is the locus line for the front view edge, that is, or the corner C dash. So from C1, I am going to drop a perpendicular projector onto the vertical plane. So once I drop a perpendicular projector onto the vertical plane, so C dash was lying on this line, so C1 dash will be obtained over here. So once you obtain this point C1 dash, so this is point corresponding to the true length of the projector or the slant edge O dash C dash. Now I am going to join O dash with C1 dash. Now I am going to join O dash with C1 dash. The moment I join this, I have been successful in obtaining the true length of the one of the slant edges, and all the slant edges will have the same true length over there. So since all these slant edges, they have the same true length, so true length is available with me. How much is that? O dash C1 dash. And how much is the edge of the base? This is equal to 35 millimeter. Now I am going to start my development from here. This is going to be my center point, which will be O dash. And then another thing I need to do, you see, these POIs, they were obtained on the apparent length projectors over here. I cannot mark those, you see, radius distances over there corresponding to O dash 1 dash, O dash 2 dash, and O dash 3 dash and O dash 4 dash, because these are the apparent length radii. So since I have measured the true length, so what I am going to do, I am going to work out the true length distances corresponding to these 4 points of intersection onto the true length over here. So once I transfer this, you see, from 1 dash 2 dash, I have drawn a horizontal line which will be intersecting with my true length over here. The moment this 1 dash 2 dash horizontal projector intersects at this true length, that is O dash C1 dash, I obtain the points of intersection actual radii. So the actual radii will be the one which will be corresponding to the true length over there. So this is the radius which is lying onto the apparent length line. But I need to draw these radii, that is O dash 1 1 dash and O dash 2 1 dash will be the radii which I will be locating onto my developed surface. Similarly, corresponding to points 3 dash and 4 dash which had been obtained on the apparent lengths O dash C dash and O dash D dash over there. So once again, since I am not using this length to draw the radial distance over here, so similarly, because I have worked out the true length radial distance, so similarly the true length radial distance for these points of intersections also need to be evaluated. So this is the radial distance corresponding to the apparent length. Now what I am going to do, once again similar to this, again I will be drawing a horizontal line over here. The moment I draw the horizontal line, so this apparent length will be transformed into the true length onto this true length line, right? So I will be getting these points as 4 1 dash and 3 1 dash onto this true length line. So I am not going to draw arcs or these distances onto the development. Rather, I want to use the true length distances of the points of intersection from the apex while I am drawing the development for the truncated, you see, pyramid over here. Now let me draw the first of all projections of the uncut square pyramid. So here I have the apex point, that is point O. From here I need to use this radius. How much is this radius? Which is the true length of corresponding to the slant generator or the slant H. This is equal to O dash C1 dash. And how much is that? You see, this is O dash C1 dash. I am not using, please see, I have ignored this apparent length, you see, radial distance over here, because this is not to be drawn. I have to use the true length distances. So I have evaluated the true length distance O dash C1 dash, and this distance I have to mark using the radius over there. So here I have drawn the radius, and then I have to mark 4 sectors over here. Every sector will be having the same edge length, which will be equal to 35 millimeter. So this is the edge length, and please see where from I am going to start. I am going to start from point A. So just see, I am going to start from point A. Second point which will be encountered on the route will be point B. Then point C will be encountered. Then point D, and then point E. And many students, what they do, they end up here, A, B, C, D. That's all. No, if you end up here, you are going to miss on the last segment over there. My starting point and the end point has to be same, because I am going to cut the solid from this point. So from D I need to go to point A, right? So once I go to point A, you see, first sector, second sector, third sector and fourth sector. So all the 4 sectors, they have been obtained. And you see, the length of the arcs to obtain all the 4 sectors is 35 millimeter, which happens to be base. So AB is 35, BC is 35, CD is 35 and DA is 35. So it's a square pyramid, so base is square, right? So now, having joined all these points over there, now I need to join them straight, because in case of pyramids, the edges have to be joined by the straight lines over there, right? So edges have to be joined by straight line. So I am going to join all these points on the base over here. Now this is the development for the untruncated, for the normal square pyramid which has not been cut by any cutting plane. Now, since this cutting plane has been cut by this AIP, now I need to mark these points 1, 2, 3, 4 over here. But it is my limitation that I cannot mark these points 1, 2, 3, 4 over here, because 1 dash, 2 dash, 3 dash, 4 dash, these points of intersection, they are lying on the apparent length. So these were the apparent length. So what I need to do, corresponding to these 4 POIs which were lying on the apparent length, I have been able to work out true length radial distances over there. And please check, O dash 1 dash and O dash 2 dash radius will be greater than O dash 1 dash and O dash 2 dash. So O dash 1 1 dash, O dash 2 1 dash are the distances which I need to measure, right? So I don't need to measure O dash 1 dash and O dash 2 dash. So I will be measuring the true length distances corresponding to these points of intersection, which happen to be O dash 1 1 dash, O dash 2 1 dash, and O dash 1 1 dash will be lying on OA. Just see, O on OA. Now I have measured this distance O dash 1 1 dash. Again I am repeating 1 1 dash. It's not 1 dash. So having measured this true length distance corresponding to the point of intersection, I am going to mark it over here. Please see, O dash. Now the first point of intersection 1 1 dash. So this point will be 1 1. So I am measuring this radius up to 1 1 dash and I am going to mark it over here. Onto OB, my second point of intersection will be lying, and what is the distance of this point from the O dash? It is same as O1 dash. So the point of intersection is 2 1 dash. So I am going to measure this distance O dash 2 1 dash and mark it at the same length over there. So this distance of 1 1 dash from O and this distance of 2 1 from O will be same, right? Then points 3 and 4. So originally they were located on the apparent length, so the names were 3 dash and 4 dash. And once again, I have evaluated the true length corresponding to these points of intersection. Now my new radius distances will be this one, O dash 3 1 dash, O dash 4 1 dash. Now I am going to ignore these distances because they were the apparent length distances over there. So the true length distances of the points of intersection 3 and 4, they are O dash 3 1 dash, O dash 4 1 dash. Now let me mark it over here. O dash 3 1 dash, it is this distance which is same as this distance on the true length. Similarly 4 1 dash is also at the same distance because the distance of 3 1 and 4 1, they are the same. So here corresponding to 3 1, I have marked a point on OC. Corresponding to point 4 1, I have marked a point on OD projector over here. So finally the last point is again 1. So whatever distance I had drawn over here corresponding to 1 1, so the same distance I am going to mark it over here. So please check, since all the 4 points of intersection originally they were lying on the apparent length, so I have worked out the true length. So here 1 1, 2 1, 3 1, 4 1 and 1 1. So all the true length distances for the points of intersection, they have been marked. So this is also true length for the slant edge, this is also true length for the base, and this is also true length for the POI. So the development which I have obtained will be giving me the true shape of the truncated pyramid over there. So now I need to join all the slant edges. You see, these are all the slant edges which I had joined in the front view. I had joined these in the top view, and you can see in this case the apparent length, and in this case apparent length is very small, but in true shape my apparent length is bigger. Similarly for this also you can see apparent lengths were for 3 and 4, they were smaller. Over here they were also smaller, but in the true length or true shape these apparent lengths have been transformed into true lengths over there. So the true lengths, they are bigger than the apparent length. So these were apparent lengths for the front view of 1 and 2. Here you see they are again very small, but here in the true length or true shape my total lengths of the slant edges, they have become bigger over there. So this is the true shape of the truncated square pyramid, right? So this way, by using the principles of projections of solids, sectioning of solids, and the principles of radial line development method, so we have been able to draw the front view of the section solid, top view of the section solid, true shape of the cut sections, or even the principles of auxiliary plane method, they have also been used in this particular problem. And then by using the radial line development method, we have been able to evaluate the true shape of the developed surface over there. And once you fold this out, you see along these slant edges, so you are going to obtain this section or the truncated solid which we had started with, right? So this is the way you can obtain the development of the truncated square pyramid. So this is all for today. So we are going to continue with further discussion on few more cases of development of surfaces in our next lectures. So thank you very much. Thanks a lot. Thank you.